So I'm going to be talking about some visualization techniques that we developed at the University of Maryland for looking specifically at bottlenecks. So these are locations on the roadway that are congested and have a queue behind them that is growing and shrinking as the congestion progresses over time. How did this all get started? So before Map 21, the I-95 Corridor Coalition, which is a collaborative effort from all of the states up and down the East Coast, wanted to identify areas of congestion and provide a consistent way to report on them to decision makers. So people in the state governments that the MPOs report to, and in the federal government. They wanted to standardize the language they were using for their performance metrics so that those decision makers could then have an easier time deciding where planning money should go. And that what came out of that was basically the Vehicle Probe Project Suite, which is the tools that they use to develop the reports that output these measures. And then Map 21 came along and made it even more obvious that this was a good idea. As basically, the federal government said, we need to standardize on what we're reporting on. And now that Map 21 is underway and they're figuring out exactly what those measures would be, we're kind of hoping that they'll settle on some of the same goals that the I-95 Corridor Coalition has already identified, so they can leverage existing functionality to continue to report on those. So for the purposes of the Vehicle Probe Project Suite, this is how we define a bottleneck. So we're looking at probe data, so data provided by INRIX at a 1-minute interval across the coalition's coverage area. We're looking at each individual location over time. So for every record that comes in, every measurement, we're looking at the speed and comparing it with the reference speed, which is generally comparable to the free flow speed at night. So basically what you'd expect to experience if there was no traffic. If conditions drop below 60% of the reference speed and hang there for a period of 5 minutes, we mark that location as a bottleneck, and we start tracking the queue building up behind that. So that's each additional segment behind it that's fallen below the 60% threshold. From there, we say that the condition is a bottleneck until the time when conditions improve over the 10-minute mark, or sorry, over the 60% threshold, and hold for a period of 10 minutes, at which point we say the bottleneck has cleared the roadway. And so that period between when the bottleneck was first detected and when it first crossed above the 10-minute threshold, the 60% threshold, is the full duration of that bottleneck. So there are a lot of groups that take advantage of this bottleneck tracking and visualization that we do. I'm going to switch over to do a live demo if that will cooperate, so I might not need the rest of these slides. Let's see what we got here. Okay, so for the operations folks, this is not necessarily the planners, this first example here. But they have access to the Vehicle Probe Project Suite dashboard, which is largely designed for looking at real-time data. So we have we're looking at DC right now. We have the colored links on the roadway indicating the current driving conditions. We're currently looking at congestion here. We're coloring based on the percentage of the free flow speed. So roughly the same breakdown that is required to detect bottlenecks. This is done because if we were to look at raw speed, like what Google Maps or another traffic map provider would currently give you, you see the 25 to 50 miles per hour, all the arterials would turn yellow, which isn't really an indication that there's any problem on those arterials because those are the speed limits. So we use this congestion percentage by default. I can turn on some other layers, so looking at the actual bottleneck locations. Each dark blue circle here represents the point of the bottleneck, and then you can see these tails growing behind them. that indicate the queue building up. I can click on any one of these to bring up details. So we're looking at the two different charts kind of overlaid together that kind of give the profile of the bottleneck so far. This one is not terribly interesting. I kind of just picked it at random. I have one over here from this morning. This is a bottleneck that occurred on the Capitol Beltway. We're looking at 6 a.m. to about 10 o'clock. This bottleneck was active. And on the chart we see here the orange axis is the travel time index, so the ratio of the current driving conditions to the expected, and the queue length is shown in green. So we can just follow this to see just how bad traffic was for anyone sitting in the bottleneck at a current time. So it kind of peaked around 8:15 when it would take you 3.5 times longer to drive through the 6-mile stretch of road that was bottlenecked there. So probably a good 18 minutes of travel time at that point. Looking at this list on the left here, I have basically a ranking of all of the active bottlenecks at the time that this was going on. We have the color behind each of these labels represents the amount of time that has elapsed since the bottleneck was first detected. So the red represents bottlenecks that have been on the roadway for 2 hours or more. Orange is 1 hour, and on down to green for very fresh bottlenecks. And then the length of the bars represents the physical length of the bottleneck on the roadway. So you can see just how badly 270 compares to, say, I-66, and so on. And kind of prioritize yourself in how you're dealing with congestion on a given day. We can also overlay traffic events, so we can see kind of where the construction might be contributing to a bottleneck. So we have an example right here where there's, it looks like 3 different bottlenecks coming off of an intersection there, and there's a construction event. So that might be something worth exploring for the operations folks if they want to try and mitigate that somewhat by contacting the construction crew. If I were to click on this button here, Generate Congestion Scan, I can pull up details about the bottleneck that is profiled here. I've got a sample of one from September 24th. We're looking at I-95. This is the stretch of road between Baltimore and Washington. It's about 30 miles of road, and it's pretty bad every single day. We are looking at the DC side down at the bottom and the Baltimore side up top. So we have little arrows indicating the traffic flow on the north and southbound sides. And the horizontal axis on each of these represents the hour of day. So what we can basically see is the green is favorable conditions for traffic, while the red is not so much. The red is your bottleneck locations throughout the entire day rather than just point in time like we were looking at before. So we can see very easily that this bottleneck was likely easily attributed to this accident that occurred at 6:45 and stayed on the roadway until 9 a.m. Though the congestion persisted until about 10 o'clock and backed up traffic for about, looks like 15 miles there. So that's incident-related congestion. And then you can see kind of your PM peak-related congestion and your AM peak-related congestion on the north and southbound sides respectively. We can adjust our thresholds for how we're coloring things in case we want to report on slightly different thresholds there. So I can be a little more restrictive in how I'm coloring things, or I can be much less so and start filtering out congestion at a much higher interval. And also toggle between looking at congestion and raw speeds so we can see how this day compares to a typical day. It looks like it's actually just about what you might expect. What's useful for more from a planning purpose is being able to compare these two congestion scans side by side. So looking at kind of your historical normal conditions and your particular day that was quite nasty. So what I've got here is two congestion scans. One is from every Thursday in September along the same stretch of road, and Thursday, September 5th, which was a particularly bad day. So I've got every Thursday in September averaged together here, and one nasty day pulled out on the right. So I can mouse over. The tooltips are linked together, which is useful so you don't have to jump back and forth to try and figure out what the difference is between the two. And I can see there that there's this nice little band, or not so nice if you have to sit in it, that is pretty consistently bad throughout the day, every day. That's actually a toll plaza outside the Fort McHenry Tunnel. So that's actually to be expected, so that's not terrible. It looks like the average September Thursday is generally okay. However, this particular Thursday, the 5th, we notice this nasty little queue building up behind our toll plaza for much farther back than expected. So that's something that we can drill into deeper and look into the cause using some of the other tools available. I'm looking at average speed. That's how we're coloring this particular plot right now. Again, I can toggle that, so I can switch to one of the other performance metrics. Looking at buffer index, which is essentially the additional amount of time that you need to account for in order to get to your destination on time, the extra time you need to add. We'll notice that now the average September day is not looking so good because of that particularly bad September 5th event, bringing down the reliability of that segment. So this is useful if you know where your bottleneck location is, what you're trying to identify. What if you don't know where you should be looking? You haven't yet discovered where your bottlenecks are. We have a tool that allows you to say, I want to search for bottlenecks in my entire state, or maybe just a particular set of counties, or on just a particular stretch of road, and specify the date range you're interested in looking at. So I've loaded in bottlenecks from all interstates in Maryland from September 1st through September 30th. So I've got a month's worth of data here. And it's gone through, crunched through that probe data, and found out where all those bad locations are, and grouped together the ones that happen in the same location, just at different times throughout the month. And it listed them out here, and I've got 38 times this bottleneck on I-695 occurred during that month, 47 this other one on 695, 81 on 495, and so on. I've got the average maximum length that each of these bottlenecks reaches, and how long it usually takes to clear the bottlenecks from the road. So that's three different metrics that are useful for kind of understanding how these bottlenecks compare to one another. They're not really comparable. You can't necessarily say that a short duration bottleneck that occurs all the time, multiple times a month, really has less of an impact than a bottleneck that occurs for a very long period of time but was only a 1 or 2 time occurrence. So what we do is we multiply the number of minutes times the average maximum length that the bottleneck reaches times the number of occurrences to come up with this kind of unitless, or at least kind of meaningless unit value called the impact factor, which allows you to rank the bottlenecks by a combination of those three metrics. So we can sort on that too. So based on this impact factor, we have a sorted list now. I can see that this 695 bottleneck is the worst. I can click on others. The map will recenter to pick out where those that new location is. I can pick up some of those others. Let me jump back to that first bottleneck we were looking at. I can resize this as needed to kind of get at what I want to look at. And focus on this diagram here. This is a time spiral. What we're looking at, the center is September 1st, and the outermost edge is October 1st. Each step out from the center is a day. It's a 24-hour clock, so you have 12 a.m., midnight at the top, 12 p.m. at the bottom, and the 6s on either side. And so every area that's colored is a time when this bottleneck, this location was in bottleneck conditions. And the color represents how long the bottleneck reached. So we can very easily see that this location is bottlenecked typically during the evening rush hour. We have almost every day, every work day rather, because you can kind of see the gap where the weekend is. At about 3 p.m., this bottleneck starts. So if you're driving through this area, you want to probably try and beat the traffic and get out of there before 3, or you're going to sit. And they clear around 7 p.m. typically. And this particular visualization is useful because it allows you to really easily spot these 5-day, 2-day trends that we're seeing here, and exceptions to the rule. So we have this bottleneck instance that was only 12 minutes long, but it was still a bottleneck. It was at this location, but it was an oddball because it happened in the morning rush hour, so people would not be typically expecting that if they were familiar with the road. I can pull up some other ones. So we can see one. This is a bottleneck that occurs typically in the morning rush hour, though not uncommon in the evening rush. This one's kind of an all-the-time bottleneck, including some late night and early morning stuff as well. I can click on any one of these bottleneck instances, and it will pull up the congestion scan for that day, and I can inspect what it is that was going on, if it's incident-related or if it's just recurring. When you're doing these metrics, you've kind of got a feel for how bad traffic is in terms of speed, but it doesn't really take into consideration, it doesn't really boil down to a single number that you can take back to a decision maker. It doesn't make a nice soundbite yet. But what we can do instead is factor volume into this, get how many people are actually sitting in these bottlenecks, and use some economic equations to figure out what the impact is to each individual user. So the end result of this, the output, is something that looks like this. So I'm looking at I-65 for October 1st through October 18th, and I've got a column for each hour of the day and a row for each date in that date range. And using those economic equations, I've calculated the total user delay cost for each of those hours. I can mouse over any one of these cells, and it'll give me the details. Each one is color-coded based on how severe the delay cost was. I can see the total cost per user, so basically dividing off that volume. I can see how many hours of delay were incurred during that particular hour. And I can see along the bottom the total cost per hour over the entire date range. And it looks like I've probably got a horizontal scroll bar here. Moving over. Yeah, there we go. I got a grand total for October, at least that portion of it, of $1.3 million, which is great to be able to take back to your state governments and say, comparing one month to the other, if you manage to reduce congestion through some program by X $1,000, they love that sort of thing. So that's all I have in terms of the visualizations I wanted to show. So I can entertain questions at this point. Yes?
Yeah, so you talk about the bottleneck impact factor.
Yes.
Which is related to the duration, bottleneck length, and occurrence. Is there any reason you do not consider either average speed of the bottleneck or delay of the bottleneck in this calculation?
Because the question was why we do not use average speed or any of the other things we could have chosen for impact factor. The impact factor is kind of meant to be more of what the impact of each bottleneck location is, rather than the bottleneck instance. And so there's a lot of averaging that goes on, and we found that keeping it at a high level, just taking in the average maximum length and the average time of the bottleneck was the simplest way to not end up kind of smoothing over everything. If we were to try and figure out what the average speed of throughout the bottleneck was, and then throughout all of those bottlenecks, we'd likely just wash everything out. Yes?
Since it's a vehicle prop project, what was the penetration rate of the vehicle prop? Like how many? Because, you know, in the end, the more data, the more vehicle props you have, the accurate the data is. But what was the...
So INRIX is the data provider for this project. They're kind of a black box. We just get the speed values off of them. We don't know where their probes are. They've said, I've heard them, I don't want to misquote them here, so I'm actually not going to. But they are paid based on how accurate their data is. There's a group at the University of Maryland that is strictly dedicated to evaluating the data coming off of this project, and they're very satisfied with it. So it's at least to the level where they feel safe trusting it.
Okay, can I add to that?
Sure.
So with this particular display is INRIX, but in other states we might be doing other. So Michigan, who's right here in the room, we're doing this for them with HEDA data. Do you have the data quality?
Sure.
Visualization? Why don't you show that? This is not a direct indication of how many probes are out there, but the coverage. So are we getting enough quality, enough samples to be able to actually generate meaningful stats? So you can see there's a few where the numbers are a little bit lower than others.
Yes?
Yeah, I was wondering, who was the targeted user of the visualization, and have you studied them using the tool actually?
The target audience is people in operations and planning, though majority of the tools are honestly more useful to the planners than the operators. We have a couple, I mean, the Michigan folks we have here, they're users. Do you guys want to say what some of the things you're doing with the tools are?
Sure. Some of the things I know with our operations centers, they do like looking at the bottleneck program because it helps them easily define the length of the queues of the bottleneck, so they know how far back they need to start changing their signs on some of that. We're also looking at a lot of this information for our work zones, whether we're seeing the expected amount of delay that was from the work zones, and then we make changes. We had made changes that, oh, we're seeing too much use delay costing us thought, so we switched from a daytime operation to a nighttime operation, and so we've seen savings from that. We're also looking at winter weather, you know, how well are we maintaining our speeds through winter storms, and looking at things on how we can, one thing that we've done is have our trucks apply salt at slower speeds, so more salt stays on the road, and you know, does that help clear the road faster, and then of course you have less use delay runs. We're also looking at incidents, trying to minimize incidents that close lanes for more than 2 hours, and so we're able to use this data and then do our post-incident reviews with our state police, our emergency responders, and then we get a good picture from these visuals of this is what's all happened, and we've seen secondary or third crashes from this. So this lane was closed for 8 hours. It really couldn't be closed for that long, and what was going on during that incident, and is there something that we can work on to shorten that duration?
Cool. Thanks, Jason.
You have a question, Tim? Yes.
Where did you get the volume data for the cost, user cost?
So the volume data is provided by, it was a joint effort between INRIX and Texas Transportation Institute. They provided some kind of baseline AADT data, average annual daily traffic, and from that we derive what the expected volumes are through each, for a given hour in a given year. We have a mechanism for users to provide higher quality volume data if they have it from probes, or rather detectors, that they've deployed throughout their state, and the user can choose to use that data instead. Mm-hmm.
Other questions? Yes, please.
So you're not using any of Maryland DOT's permanent stations, like their continuous classification or weigh and motion stations? You don't use any of that?
Not for the purposes of this project.